All right, ladies and gentlemen, welcome. We are now starting a bit on chapter 2. So let me change my pen color. Let's do that one. I always like blue. All right, so we're talking about atoms. And before we really get into atoms, we're going to discuss some of the 4 principles by Dalton that shaped our modern chemistry. And when we started going from alchemy to chemistry, we had to figure out what was true, what was not, what made more sense, and what can be proven. That's what chemistry science is we make a statement, we try and disprove it, and if we don't disprove it, we actually say, okay, it makes sense and it's real. And so Dalton came upon his atomic theory, and he made 4 postulates. Some of it came from the ancient Greeks, and he just made it more relevant for his day and age. And so let's look at his first one. All elements are made up of indivisible particles called atoms. And yeah, my English is bad at this point. Let's go ahead and put this as called. So they're called atoms. So we're talking about these small little things that cannot break apart. And he borrowed this from the Greeks and just restated this atomic theory as, this is true. But we also know that we're going to show you in this chapter that these atoms consist of 3 different parts. And we're going to talk about the protons, neutrons, if I can spell, and electrons. All right, this chapter 2 and chapter 3, we're going to focus on the protons and neutrons. And then the rest of the year, we're going to focus on the electrons, because this is where the chemistry is involved, is the electrons. Protons and neutrons give the atom's mass and identity, but the chemistry all works with the electrons, and actually all together, but we're going to show you how this interacts and relates to each other. And so this is the atomic theory then and now. Red is what we know now. And this is what theories do. They have to change with the times. We know something else about the atom. Does it mean it adopts atomic theory? Not really, but it's still true. We just have to change it up a little bit. Make an addendum to our theory, to his theory, to make it more realistic and meet our reality. And we tested it. We tested the hypothesis many times, and we found out could not disprove it, so it's going to be proven from now on. This is how science works. It's messy, but it works. Okay, the second statement. Atoms of the same element are identical, and atoms between 2 different elements are different. So what he's saying is that we have carbon and we have oxygen. All of these 2 elements are the same. This element, all the atoms of carbon should be the same. All the atoms of oxygen should be the same, and the difference between the atoms of carbon and oxygen can be determined, can be distinguished. But this is important. This is now. The atoms of the same atom are identical in the number of protons, but they can have a different number of neutrons. And this is what we're going to look more at the end of this chapter in chapter 3. It's how things change and how things can remain the same with the terms of protons and neutrons. So the masses can be different in different atoms of carbon, but the proton stays the same between carbon and oxygen, and that's what we're saying about. So protons remain the same in carbon, are identical in number, but the neutrons can change numbers. And I'm going to show you the relationship between the number of neutrons number of protons in carbon and then number of neutrons in oxygen, and how all that can relate. And that's in chapter 3, end of chapter 2 and chapter 3. So this is Dalton's atomic theory, second. Now third, this is true. Dalton's atomic theory. Atoms of different elements can mix in whole numbers to form compounds. Not half an atom, not quarter, not 1.5, but whole numbers. This is true, and it's still true. We do not have, nature likes whole numbers. Nature does not like fractions when we deal with chemistry. So knowing that, everything is whole numbers when we're dealing with ratios. Remember, a ratio is a number on top, a bar, horizontal bar, and a number on the bottom. This is what we call a ratio. This is called 2/3. And 2 can be something, and 3 can be the total of looking at something else. You need to realize what ratios deal with. And we have no changes with the third statement of Dalton's atomic theory, which is good. Now, the fourth one that we're talking about is that when we have chemical reactions occur. When they occur, atoms are separated and joined by chemical means. Atoms are not changed during this process. So, in other words, to say this, matter is not created or destroyed. And that's an E, so I can't spell. So, matter is not created or destroyed. That is important, very important, because this, when we talk about his era, a lot of people still believe in magic. And it wasn't until this statement says, hey, there's no such thing as magic. You cannot willfully create an apple out of midair. You cannot create a sword out of midair, because matter cannot be created or destroyed. That matter has to come from somewhere. And so this is true, and this helps solidify the scientific method and the scientific process, and got rid of some scientists who were charlatans trying to say, hey, I can make something out of nothing. I can make lead out of gold. You really can't, unless you have a nuclear reactor. And so we know how to do this in nuclear reactors. We do change elements using nuclear reactions. And we'll talk about that in chapter 3. So we can change elements from one element to the other using nuclear reactions and bombardment and some other techniques. But that take a lot of energy and it's a pain. So we do know that, and this is from 1945 when they made the atomic bomb. So that is true. So those are the 4 theories of Dalton's 4 atomic theories, adapted to changes in what we know. And honestly, they're still valid. Just a little bit of changes, but they still are valid. Not bad for something that's over 200 years old. Now, the question is, what's an atom? I alluded earlier, we have 3 parts to an atom. A small part, and it's the smallest part of an element. And we have protons, neutrons, and electrons. Protons are going to be positively charged. Neutrons are neutral. And electrons are negatively charged. You need to know those 3. You need to know the charges, because they're going to help us all throughout this year, actually. So we got these 3 parts: protons, neutrons, and electrons. And they're in a small little ball. And we'll talk about the structure later. I'm going to talk about that as we go through chapter 2, chapter 3, and chapter 4. Now, for most people, atoms are indestructible. In your normal life, we cannot take a piece of metal and change it to something else or break it apart. We think atoms are indestructible. Now, in chemistry, if you guys are in chemistry, we know they're going to move the electrons back and forth. That's what electricity is. So, for us, we can actually perform chemistry while using the parts of the atom, mainly the electrons. And we're going to keep stressing that throughout this year. It's the electrons that cause the chemistry. It's the electrons that bind together. It's the electrons that move back and forth. That's the chemistry. The atom just sits there. Neutrons, protons, and neutrons just sit there. They influence what's going on. Don't get me wrong. But the actual movement involves the electrons. And there's different ways that happens. And we'll talk about that throughout this year. Atoms are really, really small. These are absolutely tiny. And the radii, the radii go from the center of the atom to the outside of the atom that we know is 5 times 10 to the minus 11 to 2 times 10 to the minus 10 meters. That's actually absolutely small. Another way to say this, and I'm going to introduce something, and it's called an angstrom. This is an angstrom. Is equal to 1 times 10 to the minus 10 meters. And so this is 0.5 to 2 angstroms. And again, that is very, very small. And so when we look at going across on a copper atom, penny, if we line up copper atoms, we got a lot of copper atoms in that penny lined across. Now, we all, up to this day, we all say atoms are a sphere. We propose that. We have several prominent chemists say, hey, we think an atom is a sphere. And they have, in grad school, we learn all these relationships, all this theory about why this is true. And the thing is, it is, because we're actually able to take pictures using something called scanning tunneling microscopes. And this is an atom. I believe this is gold, but they're able to move it around and make a little pyramid out of this. So here's my atom of gold right here. And here's the diameter. So, and it looks like a sphere. So we've proven that atoms are spheres. Now, I'm going to be honest, those spheres are not solid. They're solid to us right now, but they're not absolutely solid. And there's some structure within that sphere we're going to talk about when we hit to electrons. But just want to let you know that. All right, we come to the end of this atomic structure. We got Rutherford. Discovered the atom has a nucleus. This is his experiment. He also discovered protons and were positively charged, and we call them positively charged. But right now, with this, he was influential to saying this is it on looking at atomic structure. And so we have a gold radius of 1.66 picometers or 1.66 angstroms. And so what we're doing is that we're taking these are my alpha particles, which are very, very small compared to gold, and we're going to come in, and he made a couple of hypotheses when he did this experiment that gold was going to shoot through and there'd be no deflection. And he had these hypotheses, and it was wrong, because what we see, let me change my pen color a little bit to magenta. And so what actually happens is that we get these things coming in, and they get rebounded off because gold nucleus is positive, and so is the alpha particle. And what actually happens is that we get these things flying off in all directions, some straight back. And if we look at the results, we have a lot hitting here, but we have some hit here, hit here, hit here, and actually coming straight back. And so, and to try to figure out what these results were, he realized that there had to be something small and hard in the middle, surrounded by negative. And he knew it was positive because the alpha particle is positively charged. So this alpha particle is positively charged, and the only way it was to get deflected if this thing in the middle was positive. And so what we have is that if we go back a slide to this one, is that a lot of the alpha particles were shooting by, but as it got close to this positively gold nucleus, it was being deflected. Now we know, so the question is, where are the electrons? So we assume that the electrons are floating somewhere out around this, and we'll have more experiments later, and results of those experiments will show you where those electrons are. And the thing is, the electrons did not react with the alpha particle because the alpha particle was shooting towards it very, very fast. It's like shooting a bullet at a piece of paper. It wasn't going to stop it. And so that's our results. And just to reiterate, Rutherford found the proton. Chadwick discovered the neutron. And we'll talk about those reactions and how they did that in Chapter 3. So hopefully this gives you a good idea of what we're talking about. So in summary, today we talked about Dalton's postulates or theories, and we have 4 that have been 3 have been changed. And we talked about the structure of the atom. And we left off that we have a nucleus of protons and neutrons. And the electrons are outside are around the nucleus. So that's the summary of this lecture. And we're going to talk more about protons and neutrons in our next lecture. This is a bit long. We've got enough in there for 20 minutes. And we're going to finish